Diels Alder reaction is a single-step pericyclic reaction. The reactants are diene. You see a diene here. Two alkenes in a single compound is called a diene. And then a dienophile, which is another alkene. It reacts with the diene, so we call it a dienophile. Right, so diene and a dienophile, they come from two different planes. You see the two different planes here. First plane is the plane of diene, or two alkenes in a single compound, and this is the plane of dienophile. So this dienophile is a compound that loves diene. If a compound that loves electron is called an electrophile. If a compound loves a nucleus, it's called a nucleophile. This is a compound that reacts with or loves diene, so we call it dienophile. These two planes will approach each other and start making bonds like this. The electrons from the diene will move towards the dienophile, and that forms this new sigma bond. This is the bond that's breaking, this is the bond that's forming, right? And then as a result, these two electrons in this pi bond will break and make a new sigma bond, and this is the bond that's breaking. And because now this carbon gets too much of bonds, the sigma bond will break and forms, this pi bond will break and forms a new pi bond here. So this is a transition state. If you take a picture of this compound during the transition from reactant to product, that's how it would look like, right? Bonds that are breaking and bonds that are forming are drawn using dotted lines, right? Okay, so and then the product will have the solid sigma and pi bonds. Is the sigma bonds and pi bonds that are formed as a result of this reaction. The product, diene and dienophile, reacts to get a cyclic compound. You start from a 4-member diene and a 2-member dienophile, you'll get a 6-member ring, 6-carbon ring. All right, look at the number of bonds that are changing. You started from 3 pi bonds. Okay, here's the two compounds that you're going to use in the lab. Anthracene at diene and maleic anhydride at dienophile. Maleic anhydride is a good dienophile because, okay, this is a simple dienophile. If you put two electron withdrawing groups, right, electron withdrawing groups next to the dienophile, it pulls the electron density away from the dienophile, makes it more reactive, right? So the two C double bond O's next to the dienophile, next to this alkene, makes the compound more reactive towards the Diels Alder reaction. I think this is one of the post-lab question that you want to answer. Here's the answer. The two C double bond O's next to the alkene, or electron withdrawing, makes the alkene electron deficient, which will act as a good electrophile, which can accept the electron from the diene, right? By making this electron deficient, you are making it more reactive. Okay. Now the the anthracene has three benzene rings. Benzene rings are not easy to break. They are very aromatic, they are very stable, not easy to break. So you have to give a lot of heat energy to activate anthracene to make it reactive, right? And you need to choose a solvent that can withstand that large temperature, that high temperature, right? Xylenes is one of the solvents. This is xylene. Okay, this is benzene, this is toluene, this is xylene, right? Two methyl groups on a benzene is xylene. Why do we put S next to xylene? Because the bottle of solvent we have in our lab is not one xylene, it has two or three types of xylenes. So this is another xylene. Look at the substituent methyl group, it's on a different carbon, right? And there's another xylene. Okay, so ortho, meta, para, three different types of xylenes are mixed in a bottle of in the bottle, so we call it xylenes. The xylenes have a very high boiling point, right? So they boil at 137 degrees centigrade. That is why we choose this solvent. This is also one of the post-lab question that you want to answer, right? Xylenes are a high boiling solvent. Boiling point of xylenes is 137 to 140. So we can comfortably use this solvent without evaporating it. If you use the common solvents like acetone or dichloromethane or chloroform, they all will evaporate less than 75 degrees centigrade. So you cannot apply this heat for the reaction to occur. Okay. Now that's how the electrons are moving between the anthracene and maleic anhydride. In the product, you form the new bonds, two new sigma bonds, and one new pi bond. Right? It's a little difficult to draw the product in three-dimensional shape, so you can use a simplified way of drawing it. This is not the actual three-dimensional shape. You have to bend this molecule. We will talk about that later, but this is an easier way to draw the product of Diels Alder reaction between anthracene and maleic anhydride. Now, to answer the other question in the post lab, let's go to this page. Talk about this page talks about the energy of the three benzene rings in anthracene. Okay, here's how much the each benzene ring contributes to the stability of this compound anthracene. The outer rings contributing 36 kilocal per mole to the stability of the molecule, which means to break these benzene rings, you have to add 36 kilojoules per mole of energy, right? But the middle ring, the center ring, contributes only 12 kilocal per mole to the stability of the molecule. So it's easy to break. Here's a less contributor to the stability, and these two are the significant contributors to the stability. So it's easy to break the middle ring, and that's why the reaction take place at the middle ring. Here is how the reaction take place at the middle ring. If you break the outer ring, the product would be less stable, right? If you add the maleic anhydride to the first ring or the third ring, the product would be higher in energy, in other words, less stable, right? So to get a more stable product, you have to react with the middle ring, or it automatically reacts. Maleic anhydride automatically adds to the middle ring. Because of this reason, the stability of the product is higher. Okay. Now, in the lab, we're going to use an apparatus like this, a round bottom flask, and take your anthracene. The book says add 0.22 millimole of anthracene, right, which is roughly equal to 0.039 grams of anthracene. Right, and point 0.2 millimole of maleic anhydride, which is roughly equal to 0.019 grams. It's a very tiny amount. It's very hard to weigh this small amount. Okay, so this is the maleic anhydride. Now, which one do you think is the limiting reactant? Have you studied about the limiting reactant? Okay, let's talk about this a little bit. Here's a reaction, an example reaction. A plus B gives P product. Right? 1A, 1B gives one product. 2 molecules of A, 2 molecules of B would give 2 molecules of product B. Right. 20 molecules of A, 20 molecules of B would give 20 molecules of product. What if you add 20 molecules of A plus 22 molecules of B? How much product would you get? 22 or 20? You would get only 20, right? Because you don't have enough A molecule to react. You only have 20 molecules of A to react to get the product B, because it's a 1-to-1 ratio. You need 1-to-1 ratio of A and B to get 1 molecule of P, right? So what happens to the remaining 2 molecules of B that would be unreacted? Right? So this is the product, this is unreacted reactant. So what's our limiting reactant here? A. It limits the possibility of forming the product B. Okay, so basically the reactant with less number of molecules, or less amount, not the weight, number of molecules. We're talking about the number of molecules, right? The reactant with less number of molecules is the limiting reactant that limits the product. Okay, now we don't usually talk in terms of molecules in chemistry. We talk in terms of moles. What is mole? Mole is nothing but number of molecules, 6.023 times 10 to the power 23 molecules. So let me change this a little bit. Okay, 20 mole plus 22 mole gives 20 mole product, right? 20 mole of A, 22 mole of B would give only 20 mole of B, and the remaining 2 mole of B is unreacted, not reacted, right? It doesn't have enough A to react. Okay, so again, A is the limiting reactant. Now what is mole? Mole is nothing but a number. It's a 6.023 times 10 to the power 23 number of molecules, right? Exactly. It just talks about the number of molecules, not the weight, not the volume, just the number. Like 12 means dozen, dozen means 12, a couple means 2, a mole means 6.023 times 10 to the power 23. Right. Okay, now this is a millimole. We're talking about millimoles, which means you'd add 20 times 10 to the power negative 3 times 6.023 times 10 to the power 23, right? So this is mole, this is millimole. Okay. So just an introduction for limiting reactant. So let's get back to our flask. Okay, you add 0.2 millimole of maleic anhydride. This guy is the limiting reactant, right? And you're expecting how much product? That much product, right? Okay. After this, we add some solvent. Okay, add some solvent and put a stir bar. Add a condenser because we're going to heat on a hot plate. Heat this on a hot plate. Okay, hot place. The hot plate we have in our lab will have a heating setting and a stirring setting. So it's a hot plate as well as a stirrer. Okay, we're going to heat up to 137 to 140 degrees centigrade. At that temperature, your solvent will evaporate. We don't. Our aim is not to evaporate the solvent. If you evaporate solvent, your product will be charred, right? It will be turned black and charred. So we need to bring the solvent back into the flask. That's why we have the condenser. It condenses the solvent back into the flask. Like while you're cooking, you put a lid on your pot. What it does is it just keep the steam inside your pot, and it doesn't allow your food to char, right? Keeping moisture inside your pot. Okay, condenser. And because this reaction is moisture sensitive or humidity sensitive, we need to put some drying agent on the top. Okay, drying tube. Or let me put this one. The simple way of avoiding moisture, the atmospheric moisture to getting in, is put a stopper. Put a stopper on the top. It's very simple, right? Putting a stopper will avoid moisture. But what is the problem here? You're heating, you're creating a vapor that creates a pressure, and here is a stopper. Your stopper will shoot out and put a hole on the ceiling, right? So we don't want that. We want to leave it open. At the same time, we don't want the moisture to enter into the flask. So what we do is we put some drying agent, right? A drying agent. What's a drying agent? It just absorbs moisture. When you buy new electronics or new shoes, you'll see a packet of silica, inside your package, right? That is a drying agent. It keeps the moisture, because moisture will make your new shoe or new electronics not good, right? So moisture will affect that. Having a silica will keep a dry, nice product. Okay, like that, we have a drying agent here, that is calcium chloride, CaCl2, which absorb the moisture. If the air tries to enter into this way, the calcium chloride will absorb the moisture and keep this flask moisture free. On the top, you can put a stopper on, no problem, because you have an opening. You have an opening here. If you create an extra pressure inside the flask, the pressure will leak out this way, right? As calcium chloride is not a stopper, it just a tiny beads, you still have a way to go out and the air to get in, right? Okay, on the top you can put a thermometer to measure your temperature, right? That's it. That's a heating setting. It probably takes 30 minutes of heating. After that, we will separate the product from the solvent and the unreacted product through filtration setup.